Imagine a time when one country ruled the semiconductor world, then lost it all. In the late 1980s, Japan produced over half of the world's chips, yet today it makes less than 10%. Now, picture a remote lab in northern Japan where engineers are firing up a machine that costs as much as a jumbo jet, trying to build a chip measured in atoms. It sounds like science fiction, but it's happening. Japan is attempting a dramatic semiconductor comeback, betting on a startup called Rapidus to leap from a 40-nanometer legacy all the way to cutting-edge 2-nanometer chips. The obvious question is, can this bold gambit bring Japan back to the top of tech, or is it too late? In the 1980s, Japan's semiconductor industry reigned supreme, supplying memory chips and components to the world. But a combination of factors, from business strategy missteps to global competition, caused its crown to slip. Japanese firms stuck to the traditional integrated device manufacturer, IDM model, doing everything in-house, even as the world moved to specialized foundries like TSMC. Investing continually in bleeding-edge fabs proved too heavy a burden for Japan's electronics giants, and by the 2000s, they fell behind. Meanwhile, newcomers like Taiwan's TSMC soared by focusing purely on manufacturing and achieving massive scale. The result? Japan's share of the global chip market withered from around 50% to around 15%. By the 2010s, the most advanced chip made on Japanese soil was a humble 40-nanometer node, while Taiwan and South Korea churned out 7 nanometers, 5 nanometers, and now 3 nanometers chips. The wake-up call came during recent crises. A global chip shortage that hit after a Texas cold snap and a factory fire in Japan halted production of cars, hot water heaters, even bank cards. Supply chains buckled, and Japan realized its economic security was at stake if it couldn't secure advanced chips at home. In response, the government launched a new semiconductor strategy focused on 2 tracks: invite foreign leaders to build fabs in Japan, and foster domestic champions for the most advanced technologies. One example of the first track is JASM in Kumamoto, a joint venture where TSMC, Sony, Denso, and Toyota built a fab producing 12 to 16 nanometer chips, operational by 2024. But while that brings know-how, it doesn't put Japan at the cutting edge. Enter the second track. Rapidus Corporation, a new company with an ambitious mission to mass-produce 2-nanometer chips by 2027 and put Japan back in the tech vanguard. Rapidus, Latin for rapid, was founded in 2022 as a unique public-private venture to spearhead Japan's return to the semiconductor frontier. It's backed by a consortium of 8 corporate giants, including Toyota, Sony, NTT, SoftBank, NEC, Kioxia, Denso, and Mitsubishi UFJ Bank, who together invested a modest 7.3 billion yen, approximately $51 million, to get it started. If that sounds small for a chip fab, that's because the heavy lifting is being shouldered by the Japanese government, which has committed unprecedented support. So far, public subsidies total 920 billion yen, over $6.5 billion for Rapidus, part of a broader 1.72 trillion yen, $12 billion package Japan has earmarked to revive advanced chip manufacturing. In short, Tokyo is all in on Rapidus, seeing it as crucial for national security and tech leadership. As Prime Minister Fumio Kishida declared in late 2022, the government will fully support investment in semiconductor mass production in Japan. The vision for Rapidus is audacious: to establish a pilot line for 2-nanometer chips by 2025, then achieve mass production in 2027. If successful, Rapidus would become the world's 4th manufacturer capable of making such chips at scale, joining the exclusive club of TSMC, Taiwan, Samsung, South Korea, and Intel, USA. For Japan, which hasn't run a leading-edge fab in decades, this is truly a moonshot. Rapidus broke ground on its state-of-the-art fab in Chitose, Hokkaido in September 2023. In remarkably short time, by April 2025, the company announced it had powered up a pilot production line for 2-nanometer chips and performed first test runs on newly installed equipment. Inside the gleaming facility, over 200 pieces of cutting-edge equipment, including a $300+ million extreme ultraviolet EUV lithography machine, are now in place and ready for operation. This milestone marked the start of Rapidus's journey from lab to fab. As Rapidus's US subsidiary president Henry Richard marveled, "We broke ground in 2023. It's pretty amazing that by Q2 2025 we made first exposures on the EUV system and are ready to start pilot production." This rapid progress owes a lot to planning and partnerships. Even before shovels hit the ground, Rapidus secured a strategic alliance with IBM, the very company that demonstrated a 2-nanometer test chip in 2021. In December 2022, Rapidus and IBM announced a joint development deal. Rapidus would leverage IBM's breakthroughs in 2-nanometer nanosheet transistor technology, and in exchange, IBM would gain a new manufacturing partner. Essentially, IBM provides the recipe. Rapidus will cook the chips. To absorb this know-how, over 100 Rapidus engineers have been dispatched to IBM's Albany Nanotech complex in New York, working side by side with IBM researchers on 2-nanometer process R&D. Rapidus will leverage IBM's semiconductor R&D leadership, including 2-nanometer node technology, the companies declared, as they set up a timeline for technology transfer. The roadmap: joint development in Albany, already underway. Transfer of the 2-nanometer process to the new fab in Japan by around 2025, and pilot production shortly after. By July 2025, Rapidus expects to produce its very first 2-nanometer test chips, a major step toward proving the process can work on the new line. Why 2 nanometers? To put it simply, 2 nanometers is tomorrow's technology. No one is mass-producing it yet, but it's expected to power the next generation of everything from AI supercomputers to smartphones. A nanometer is a billionth of a meter, so these chips have features just a few atoms wide. In fact, a 2-nanometer transistor gate is roughly the width of 10 silicon atoms. Shrinking to this scale promises big payoffs. Chips that are faster and far more power efficient. For example, experts project that 2-nanometer chips could cut power use by over 30% compared to today's 3-nanometer devices. That's huge for power-hungry data centers and battery-powered gadgets alike. But it also represents uncharted territory. As Rapidus's Yukiko Shindo notes, the architecture of the 2-nanometer chip is totally different from that of the 3-nanometer, a blank slate challenge for all players. This critical juncture is a prime opportunity to break into the market. In other words, 2 nanometers is so new that even the current industry leaders are facing a fresh learning curve, giving an opening for newcomers like Rapidus. Rapidus isn't going it alone. Its very structure is a who's who of Japanese industry coming together in an all-Japan effort. Each player brings something to the table. IBM, USA, R&D powerhouse. IBM's research arm pioneered the 2-nanometer nanosheet transistor and holds critical patents. IBM is essentially Rapidus's technology mentor, providing the process technology and expertise. Without IBM's head start, Japan couldn't attempt 2 nanometers this fast. Toyota, manufacturing excellence. As the world's premier car maker, Toyota is legendary for its production system, just-in-time and total quality control. Toyota's investment isn't just cash. Its expertise in efficient, high-precision manufacturing could help optimize fab operations for yield and throughput. Moreover, Toyota has a vested interest. Future autonomous and electric vehicles will need high-performance chips, and a domestic source is strategically appealing. Sony. Semiconductor experience. Sony is one of Japan's few tech companies still thriving in chip design, especially image sensors, where it's a global leader. Sony can contribute its materials and imaging know-how. For instance, Sony's semiconductor unit understands high-grade silicon wafers and photoresists crucial for advanced nodes. Sony might also be a future customer. Imagine 2-nanometer chips powering next-gen image processors or PlayStations. NTT and SoftBank, telecom and AI users. These giants ensure end-user perspective. NTT, Nippon Telegraph and Telephone, needs advanced chips for 6G networks and data centers, while SoftBank, which owns ARM and invests in AI startups, might channel customer demand for cutting-edge chips. Their presence signals that Rapidus's 2-nanometer chips have built-in demand from Japanese telecom, cloud, and AI sectors. Denso, automotive components. As a major auto parts maker and Toyota affiliate, Denso's involvement ties into the automotive use case, much like Toyota's. It underscores Japan's focus on securing chips for smart cars and transportation systems. Kioxia, formerly Toshiba Memory. Memory integration. Kioxia is a flash memory manufacturer. While Rapidus is about logic chips, having Kioxia on board opens possibilities for collaboration in advanced packaging, like integrating memory and logic together. It also demonstrates Japan's all-hands approach, bringing even competitors under one tent. NEC and MUFG Bank. NEC, tech conglomerate, adds technical breadth. NEC has history in semiconductors and supercomputers. And MUFG Bank, one of Japan's largest banks, adds financial backing. Their participation shows financial and corporate support beyond just tech companies, a national project in spirit. This diverse consortium is unprecedented in Japan, where companies historically acted more independently. It reflects a lesson learned. To beat TSMC or Samsung, Japan Inc. must unite its best resources. Japanese companies have abandoned their focus on IDMs and are playing a part in the international division of labor through cooperation, notes Professor Kazuto Suzuki, pointing out this shift from insular thinking to global collaboration. Crucially, Rapidus's ecosystem extends far beyond its investors. The company is forging ties worldwide to access top talent and tools. Besides IBM, Rapidus partnered with Belgium's IMEC, a renowned semiconductor research hub, to tackle challenges like next-gen EUV lithography. It's collaborating with Germany's Fraunhofer Institute and Singapore's A-Star on advanced chip packaging and chiplet integration. And through Japan's new leading-edge Semiconductor Technology Center, LSTC, Rapidus plugs into a network connecting to the US National Semiconductor Technology Center, France's CEA Leti, and more. In short, they are tapping every source of expertise available, wherever it may be in the world. Equally important is Japan's domestic supply chain strength. Although Japan lost ground in chip manufacturing, it still dominates in semiconductor materials and equipment. Rapidus can leverage homegrown suppliers for ultra-pure silicon wafers, chemicals, and machinery. Companies like Tokyo Electron, a top producer of etching and deposition equipment, and Screen Holdings, cleaning tools, are likely key providers to the new fab. And while Japan's own lithography maker, Nikon, fell behind ASML in EUV, other Japanese firms lead in niche tools and metrology, measuring chip features. In fact, Rapidus's Hokkaido fab is sparking a cluster. Global equipment giants ASML, Lam Research, and Applied Materials have all decided to set up bases around the Rapidus site. The vision is a high-tech hub in Chitose that gathers suppliers, research institutes, and talent from around the world. A modern twist on Silicon Valley, but in northern Japan. The new plant, projected cost 5 trillion yen, or approximately $35 billion to fully build out, is even imagined as a green and digital transformation hub for the region. with sustainability and smart infrastructure built in. Beyond partnerships and funding, Rapidus is also innovating in how to make chips. Rather than simply copying TSMC's playbook, Rapidus is pursuing a different manufacturing philosophy to try to level the playing field. One key difference: single wafer processing. Most big chip makers run their fabs like high-speed bakeries, processing wafers in large batches for efficiency. They load a lot of wafers into a machine, run the process step on all of them, then move them along together. This maximizes throughput when you're making millions of identical chips. Think smartphone CPUs. However, it also means long lead times and inflexibility. If you want a few specialized chips, you wait in line behind the big orders. Rapidus plans to break from this model. As the company describes, it will use a single wafer process, treating each wafer independently at each step. Wafers will still flow through the fab, but not as fixed batches. Each wafer can get a custom recipe or faster handling if needed for a particular client. Why do this? Flexibility and speed. Rapidus is targeting customers who need smaller lots of chips fast, such as AI startups iterating new designs, research labs, or specialized industries. The big three foundries, TSMC, Samsung, Intel, are optimized for huge volumes. They often have high minimum order quantities and long turnaround times. Rapidus sees an opportunity to serve the market that needs 100 wafers with a custom chip now, not 10,000 wafers a year from now. By processing one wafer at a time, Rapidus can potentially churn out prototypes or niche products quicker, without waiting to fill a large batch. Smaller batches and speed. Both would be great for any product in early development. One industry observer notes, though conceding that this won't be a low-cost approach. Rapidus isn't aiming to compete on cost per chip initially. It's competing on agility. Of course, single wafer processing could slow total throughput, which is why Rapidus pairs it with another strategy: design manufacturing co-optimization, DMCO. This is essentially merging the chip design and fab feedback loops into one cycle. In a normal foundry model, a customer designs a chip, the foundry makes it, and only after weeks of production do you get data to see if the chip meets specs and yields well. Rapidus wants to tighten this loop dramatically. They plan to use AI and a plethora of sensors throughout the fab to monitor each wafer in real time, measuring temperatures, chemical reactions, overlay accuracy, you name it. All this data will be fed back into the design and process tuning. In essence, the chip's design can be tweaked in tandem with the manufacturing process to quickly improve yield and performance. This will enable us to measure the processing of individual wafers, learn from the results, and quickly feed the data back into the system, explains Henri Richard. By continually adjusting parameters on the fly, Rapidus aims to shorten the time and wafers needed to reach high yields. It's like having a self-correcting assembly line that learns and improves with every wafer processed. University of Tokyo professor Tadahiro Kuroda calls this vision the ideal scenario in semiconductor manufacturing, using big data to ramp up yields faster, thereby shortening time to market for new chips. Another innovation in the Rapidus fab is a grid transport system for the wafers. Traditional fabs move wafers along a fixed route, a bit like a train on rails. If one machine in the line goes down, everything behind it must wait. A traffic jam on the semiconductor highway. Rapidus claims its fab has a more flexible transport network that lets wafer pods reroute to any available tool, avoiding bottlenecks. Imagine an autonomous vehicular system for silicon wafers, where if one road is closed, they take a different path. This is meant to maximize equipment uptime and keep those single wafers flowing smoothly, further offsetting the slower batch throughput. These approaches are unproven at scale, and Rapidus is essentially test driving them on one of the most complex manufacturing challenges ever: 2-nanometer chips. It's a high-risk, high-reward approach. If it works, Rapidus could carve out a unique niche, being the go-to foundry for custom, cutting-edge chips with quick turnaround. It's a different value proposition than simply trying to match TSMC's volume or costs. And given the explosive demand for AI accelerators and advanced semiconductors, there may be a market for this model. There will be a great need for 2-nanometer chips, Professor Kuroda notes, especially as generative AI and data centers drive enormous growth in compute demand. Those leading-edge chips also promise significant energy savings, 30% plus efficiency gains, which is crucial as power consumption becomes a limiting factor. In short, Rapidus is betting that demand will far exceed supply from the existing giants, leaving room for an agile newcomer, even one that might be a node behind initially. No renaissance comes without its trials. For all the promise of Rapidus, immense challenges loom on the road to 2027. It's time to address the potential pitfalls and skeptics' questions head-on. What could go wrong? 1. The funding gap. Building and running a leading-edge fab is astronomically expensive. Rapidus itself estimates needing around 5 trillion yen, $35 billion, to reach full mass production at 2 nanometers. Yet, as of now, the company's funding is only a fraction of that. The Japanese government's subsidy of 1.7 trillion yen is significant, but still only about 1/3 of the projected requirement. Private investors, so far, have been cautious. The founding 8 firms put in just 7.3 billion yen, and even a planned infusion of 25 billion yen from major banks in late 2024 is a drop in the bucket. This lack of big private money raises concerns over Rapidus's future, IEEE Spectrum notes bluntly. It harkens back to the early days of TSMC, which also relied on government vision when local companies were hesitant. The Japanese government even considered offering guarantees to attract private investment, effectively saying, "We'll back you if you back Rapidus." However, political changes stalled that initiative. Going forward, continued government support is essential and perhaps inevitable if Rapidus is to bridge the funding gap. Without deep pockets to sustain multi-year losses and multi-billion upgrades, even the best tech could falter. This means Rapidus must prove its viability quickly to unlock more funding, a classic race against the financial clock. 2. Talent and workforce. Money can buy machines, but not experienced engineers overnight. Semiconductor manufacturing expertise is rare and in high demand globally. Japan's domestic talent pool for cutting-edge process engineers largely dissipated after the 1990s. Rapidus has tackled this by sending engineers to IBM for training and hiring aggressively. 20 to 30 new employees are joining Rapidus each month, all sharing the strong desire to accomplish the same goal, according to HR manager Shindo Yukiko. The company has inked agreements with Hokkaido University and other institutes to develop curriculum and training pipelines. By the time the Hokkaido fab is fully operational, it's expected to involve several hundred engineers from Japan and abroad. Still, the question remains: can Rapidus recruit enough skilled people fast enough? The global competition for chip talent is fierce. The US, Taiwan, and Europe are all scrambling to train and import semiconductor engineers. One of the keys to surviving international competition is to acquire the requisite labor force, Professor Suzuki emphasizes. Rapidus may need to poach talent from overseas or convince Japanese expatriates to return home. And it's not just engineers for the fab, it's also tool maintenance experts, software specialists for that DMCOAI, and a whole supply chain of technicians. Any shortage or skills gap could become a bottleneck when ramping production. This is a human challenge as much as a technical one. Third, technological risk. Even with IBM's help, making 2-nanometer chips at high volume is extremely hard. Rapidus is not only deploying a brand new process, nanosheet transistors, but also doing so with those untested methods, single wafer, DMCO, etc. There's a real possibility of teething problems, unforeseen technical hurdles that delay progress. This could range from lower than expected yields, too many defective chips per wafer, to equipment integration issues to software bugs in the AI optimization. Each of those could extend the time it takes Rapidus to get viable products out. Recall that even Intel, a seasoned chip maker, stumbled for years on its 10 nanometer node, and Samsung had yield woes at 3 nanometers. For a newcomer, the challenge doubles. Rapidus has basically a 2-year window, 2025 to 2027, to go from pilot to volume production. Technically, the success of Rapidus hinges on whether the semiconductor prototypes being developed for mass production in 2027 progress smoothly, says Atsushi Osanai, a business professor in Japan. Any significant glitch in that progress could mean missing the 2027 target, which might shake stakeholder confidence or cause partners to lose patience. The upside is that Rapidus has hit its early milestones on schedule so far. Pilot line in April 2025, test chips in 2025, building credibility that they can execute. But the hardest part, high-volume manufacturing, still lies ahead, and it's an unforgiving arena. Fourth, competition and timing. By aiming for 2 nanometers in 2027, Rapidus is by definition playing catch-up. TSMC and Samsung are set to begin 2 nanometer mass production around 2025. In fact, TSMC has already announced development of 1.4 nanometers, next-gen, with plans to start production by 2028. This means that by the time Rapidus is selling its first 2 nanometer chips, the incumbents might be a full node ahead. How can Rapidus compete? Here the strategy is not to go head-to-head on volume or beat TSMC to the next node, but to offer something different: the flexibility, the dedicated service, and simply additional capacity to a supply-constrained market. If the demand for advanced chips is so high that TSMC, Samsung, Intel can't fulfill all orders, a scenario some find plausible given the AI boom, then Rapidus can find customers even if its tech is a tad behind the very bleeding edge. However, if the giants execute perfectly, they could undercut Rapidus or lock in the top customers, like Apple, Nvidia, etc., with their own capacity. Rapidus then might be relegated to lower margin or sporadic orders, which would hurt its finances. As of mid-2025, Rapidus has moved from a bold idea to a tangible reality. A new fab rising in Hokkaido, a pilot line operational and prototype 2 nanometer chips imminent. It's an achievement in itself. 2 years ago, Rapidus didn't even exist. Yet the hardest part lies ahead: scaling up to mass production, on time, and on budget. The company must hit near-perfect execution in technology, attract more funding, and cultivate a skilled army of engineers, all while the global chip race keeps accelerating. If Rapidus pulls it off, the payoff is enormous. Japan would regain a seat at the table of advanced chip makers, ensuring its industries, automotive, electronics, AI, have secure access to top-tier semiconductors.